Here we're going to talk about sound intensity, but a little bit of review of the Doppler effect first. A source of sound will emit sound with a constant frequency. However, if the source is moving, then the apparent frequency of the source will be different from the true frequency. So if the apparent frequency of the source is higher than the true frequency, then what is the source doing? Is it A, moving toward you and you're stationary, or the source is stationary and you are moving toward it? Or could it be either case, A or B, or neither A nor B? Either A or B. Sorry, that didn't work out very well. Let me redraw that. Either A or B. So choice C is the best choice. So it could be that you are stationary and the source is moving toward you, or could be that the source is stationary and you're moving towards the source. As long as you're moving towards each other, this is the case. The frequency of the sound that you hear is higher than the true frequency of the emitted sound. Think of it this way. Here's the source of the sound. Could be a car, like this really cool hot rod, and it's honking its horn with a constant frequency. You're standing stationary at rest on the side of the road. In front of the vehicle, every time a new wavefront or compression is emitted from the honking horn, the car is a little bit closer to the last wavefront that was emitted than it would have been if the car weren't moving. So really, in a sense, the car is catching up to those wavefronts, and they kind of bunch together in front of the car. So that means that since the speed of sound is constant, the frequency has increased. In other words, the number of compressions that hit your ear each second will be greater than it would have been if the car were standing still. Behind the car is moving away from each of those wavefronts, and so they're spreading out instead of bunching together. So that means that the wavelength increases behind the car, the wavelength decreases in front of the car for the person who's hearing the sound. So you hear a higher frequency sound in front of the car. If you were back here, like this blue person, you would hear a lower frequency sound. And that's why when the car goes by, you hear as they honk the horn at you, because of the Doppler effect. Sound intensity is something a bit different. It's not about the frequency of the sound, nor is it about the wavelength. It's about energy. And the energy of a wave depends on its amplitude. The amplitude of a wave depends on the amplitude of the vibration at the source. And that's all about energy. So the more energy there is at the source, or the more work is done to move the medium or displace the medium at the source, the more energy the wave will have. So the more energy the wave carries. Think of it this way. If a huge boat goes by on the lake, then that's going to do a lot more work on the water than a canoe would. And so the large boat generates much higher amplitude waves, and you get lots of wave energy crashing into the shore when those waves reach the shore. If someone paddles by in a canoe, you may not even notice those waves because the amplitude is so low, which means that they carry very little energy. Intensity is really the amount of energy that is striking a given surface area each second. So intensity of sound can be found by taking the energy of the sound wave and dividing by the area times the time. Or if you want to think of it this way, it's the energy divided by the area, and then you can take that answer and divide by the time. Of course, we know that energy over time is just power, so another way to write intensity is just power divided by area. The standard units for sound intensity are watts per meter squared. That's not just for sound intensity, but generally speaking, those are the units for intensity. We most often encounter them with sound waves, though. This diagram shows you really how it works. If you imagine a source of sound right here at P, like a loudspeaker that transmits sound equally in all directions, then whatever energy is emitted from the very spot where the sound is emitted, all that energy will be spread out equally in all directions. So if you move some distance away, say this distance away, then all that energy is spread out over this sphere right here, this entire area. And we know that the area of a sphere is 4 pi r squared. So we can take the power that's emitted at the source and divide by that area, and that will give us the intensity. And of course the surface area, as we can see here, goes as r squared, which means that the intensity varies inversely as the square of the radius of that imaginary sphere, because the area gets bigger and bigger and bigger of this imaginary sphere as we get further and further from the source of sound. So that's the math of it. If we want to just describe it, we could say that the intensity of the sound drops off or decreases rapidly as we move away from the source. That's why it's so dangerous to have headphones on that have a really high power, because the distance, r is really, really small, and if r is really, really small, the intensity is really, really big, and you can damage your ears that way. So we call this the inverse square relationship, and we see this a lot in physics. There are a lot of concepts in physics that follow this rule. We also sometimes call it the inverse square law. Gravity follows this law. The electromagnetic forces follow this law. And there are other forces as well. The intensity of light, in fact, the intensity of any kind of radiation follows this law. So it's very common. So if the distance from the source is doubled, this law tells us that the intensity will be decreased by a factor of 2 squared, or 4. If the distance were tripled, then the intensity is decreased by a factor of 3 squared, or 9. And you can see just how quickly this intensity drops off. Now, humans have pretty sensitive ears. We can hear sound waves with very low intensity. 1 times 10 to the minus 12 watts per meter squared, in fact, is, on average, the lowest intensity sound we can hear, which is extremely quiet, if your ears are in really good shape. Mine are not, so I probably can't hear sounds that quiet anymore. So 1 times 10 to the minus 12, that's a tiny amount of energy. That's 1 picowatt per meter squared. This is a more technical description of how much pressure that kind of wave has. Very tough to detect. So our ears, when we first get them, are incredibly sensitive. There's a special name for this intensity. We call it the threshold of hearing. Now, we can hear, as humans, we can hear a very wide range of intensities. We can hear something with as little energy as what we just saw, the threshold of hearing. And the sound that we hear that is most intense, so the most intense sound which we can hear without suffering permanent damage to our ear, is more than 1 billion times more intense. So that's a very wide range of sound intensities. So for convenience, physicists will often use a different kind of scale. Instead of using this huge range, they'll use a logarithmic scale, which is based on powers of 10 for intensity, and we call this sound level. You've probably heard of this before. It's called the decibel scale, small d, capital B. So the threshold of hearing is given the value of 0 decibels. Since we want to describe how humans hear, we just take that as being 0 decibels and we start the logarithmic scale there. Which means that there are sounds that occur with a sound level which is less than 0 decibels. It's just that people can't hear them. So here's an example of a sound which is about 10 times more intense than the threshold of hearing. So about 1 times 10 to the minus 11 watts per meter squared. Rustling leaves. So that's about 10 decibels. A whisper, which is about 100 times more intense, has a sound level of, well, you'll notice here we've multiplied by 10 the value of sound intensity to get a value of 1 times 10 to the minus 10 watts per meter squared. And so the new sound level is 20 decibels. So you can start to see a pattern here. We multiply the sound intensity by a factor of 10, and to get the new value for sound level, we add 10 decibels. A sound which is 1,000 times more intense, or 10 times 10 times 10, or 1 times 10 to the minus 9 watts per meter squared, is assigned a sound level of, well, what do you think that's going to be? We've multiplied again by 10, so this one will be 30 decibels. So again, every time we multiply the sound intensity by a factor of 10, we add another 10 decibels. So we go, in this case, from 20 decibels to 30 decibels. So if one sound is 10 to the x times more intense than another sound, then it has a sound level which is 10 times x more decibels than the less intense sound. Here's an example. A mosquito's buzz is often rated with a decibel rating of 40 decibels. Normal conversation is around 60 decibels. How many times more intense is normal conversation compared to a mosquito's buzz? About 100 times. Now, why is that? Well, to go from 40 decibels to 60 decibels, we had to add 20 decibels. So if we added 20 decibels, that must mean we added 10 twice. If we added 10 decibels twice, then for the sound intensity, we should multiply by 10 twice. So 10 times 10 gives us 100 times the sound intensity that we started with. Here's another one. Someone standing 1 meter away from a busy street measures the decibel level of the traffic to be 70 decibels. What level would they measure if they were standing 10 meters away? Well, it would have to be 50 decibels. 10 times further away, the area has now decreased by 100, thus decreasing the intensity by a factor of 100. So the area has increased by a factor of 100, and so the intensity has decreased by a factor of 100. Well, what's 100 again? Well, 100 is 10 times 10. So if we're multiplying the sound intensity, or if we're, in this case, we're dividing the sound intensity by 10 twice, then we have to subtract 10 decibels twice. So if I take 70 decibels, I subtract 10 decibels, and then I subtract another 10 decibels, and we get 50 decibels. Sometimes you'll hear sound described with loudness. Loudness is really just our subjective description, how we hear the sound based on its intensity. And that can change with frequency as well, because our ear is more sensitive to certain frequencies than to others. This graph shows you how intensity decreases as the frequency increases to about 800 hertz or so, and then it increases a bit around 1,000 again, and then decreases again, and then increases again. So as you listen to sound with changing frequency, even if the intensity from the source is the same, to you it may sound louder at certain frequencies than at others, just because of our ear's response to different frequencies. High intensity sound waves that have really large amplitudes can damage the ear because they cause really large amplitude vibrations in the ear. We have tiny little sensitive hair cells inside our ear in a tube called the cochlea. And these hair cells can be damaged if they're exposed to high amplitude vibrations. So you can become selectively deaf to certain frequencies if you are working in an industry, for example, in which your ears are exposed to sounds around 700 hertz over a long period of time. If those are intense sounds, then you could lose the ability to hear in that range because the hairs in your cochlea have been damaged at those frequencies. How do we know if a sound is too loud? Well, regular exposure to 110 decibels for more than a minute or to 100 decibels for more than 15 minutes can risk permanent hearing loss. If you're exposed to sounds above 85 decibels for a prolonged period of time, that can cause gradual hearing loss, and most MP3 players have a maximum volume setting equal to about 105 decibels. So if you listen to loud music for long periods of time with headphones on, then you run the risk of having permanent ear damage over time. So headphones can be the most destructive because they don't filter out any external sounds, which means you may be tempted to turn the volume up, and they're also positioned really close to the eardrum. So the area of that imaginary sphere is really small. So you're dividing the power by a small area. So if I'm dividing the power by a small number, then the intensity becomes a big number, and that can eventually damage your eardrums. Alright, now we're going to try an activity in which you're going to measure sound level for a variety of sources around the building. And we'll see how we do.